right, so kind of our strategy today is going to be to graph the function. If possible, do it by hand, shade the area of interest, and then the integral to find the area. Sometimes I have to find the limits of integration, and that would be where the curves meet each other. So we're going to find the area region bounded by the graphs of g of x equals 0. That's just a horizontal line. And then 3 minus 2x minus x squared. So where would that region be? Those were its boundaries. This parabola on the x-axis. I'll shade it or highlight it. Okay. Now in this is just with the x-axis, and so this really is no different than how we found area before. I do need to find where these points occur, and it looks like I know where they occur, but let's make sure I do. So I'm going to set f of x equal to 0. That's this function. I'm going to have to factor it or use quad formula. This is I don't like a negative leading coefficient, so I'm going to multiply both sides by -1. Okay, that leaves me with -3 plus 2x plus x squared. Oops. I'm going to put this in the middle. This should, let's see, -3, shouldn't it? All right, yes, you can use quad formula, but this factors nicely. What does it factor into? Good. And now let's confirm, does that match up with what I see there? Yep, there are zeros at x equals and x equals -3. That just gives me my limits to integration. The limits are the top and bottom of the integral sign. So I'm going to go then from -3 to 1, and I'm just finding the area under the, which is f of x dx, which means if I want to do this algebraically, which I can, I am going to integrate it. What's the antiderivative of 3? 3x. What's the antiderivative of -2x? Minus x squared. And how about this? Yep. -x cubed over 3. Sorry about those weird negatives. I don't know what's going on there. And we're going to do this from 1 to -3. So this is some good practice. Fractions. All right, if I put the 1 in, let's just practice putting the 1 in. If I put in the I have 3 minus 1 minus 1/3. You following? And then when I put the -3 in, so I'm doing right now antiderivative of 1 minus antiderivative of -3. If I put the -3 in, this would be -9 minus 9 minus a -27, which is also 9. Okay, be careful of negatives here. Okay. So this is -9 minus 9 plus 9. This is just, yeah. There's a lot of negatives in here. All right, so let's simplify a little bit. If I can avoid having to do like common do. 3 minus 1 is 2. 2 minus 1/3, isn't that 1 2/3? Okay. And we already agreed in here, what is this equal? -9 minus 9 plus 9. 9, agreed? So this is minus a -9, which is plus 9. It looks like we are looking at 10 and 2/3 for that area. All right, so let's make it a little more difficult. What is the region that I would shade for number 2? So it's like I have this little curve right here. And so I'm going to need to find these things. To me, this looks like 0. This looks like 3, but we'll confirm in a second. When I'm finding the area, I want you to think of it this way. It would be, if I thought about the parabola for 3, we're going to assume it's 0, 3, I'll show you in a second. The whole area under the curve is where I'm shading right now in the dark color, okay? If I took out the area 9, do you see how I'd be left with the yellow piece, which is what I want? So in a minute, I am going to take the integral of the top curve, which is f of x minus g of x. I'm going to go ahead and write that down so you understand what I'm going to be doing. And then just to make sure I have the right spots, I'm going to find where these curves meet. That would be where they're equal. So if I moved the left over to the right, I don't like negative coefficients. That's why I would have x squared. If I would subtract 4x, I would have minus 3x. Are you following me? And this 2 is 0. So then I could just factor an x out. Looks like I meet at x equals 0 and x equals 3. So now I'm going to go ahead and make those my endpoints of integration. Now, there's different things you could do. You can break this integral apart if you want, because really that's what you're doing. You're doing these separately. You can put them together, okay, when you have subtraction. And you can even write a simplified expression. That's what I'm going to do because I think it's going to be easier. To me, instead of trying to integrate that and then trying to integrate that and plug in the numbers and subtracting them, if we subtracted these two functions first, we'd get a simpler function to work with. So what is f of x minus g of x? Well, negative x squared minus nothing, negative x squared. 4x minus 1x is 3x. 2 minus 2 is 0. Okay. So now I have something that's going to be less time consuming rather than integrating both of those other things. What's the derivative of negative x squared? Negative 1/3 x cubed, or negative x cubed over 3. And how about 3x? 3 over 2x squared. Like, at least we only have to do 3, because what's going to happen when I plug in 0? It's going to get 0. When I put in 3, I get, once again, that was similar to what I had before, negative 27 divided by 3, right? So that has to be negative 9 plus 3 times 3 squared would be 27 over 2. How do you want to handle this? You do? Okay. If you wanted to change this to 13 and a half minus 9, you can do that too. He wanted to, we'll be like Aiden. It's a good goal. Top and bottom by 2. So I'm just finding a common denominator. Negative 18 over 2 plus 27 over 2 is positive. Okay. Now, I know that graph probably aren't going to maybe graph this by hand, so we're going to look at a picture of the graph. Okay, we can integrate this by hand though. It's awesome. Let's look at the graph. You can just look at my graph and I'll transfer it for you. So secant is 1 divided by cosine, right? And sometimes we see this written as, correct? Okay, and what that means is we square the whole cosine. Your calculator is smart as long as you close the parentheses, that this is squaring the cosine. And then here is sine of x. I know we were doing degree stuff earlier on, so when I'm picking a window, I'm going to just go 0. I'll go a little bit beyond. You want me to do pi halves? Sure. I'm not going to make this very big because sine goes to 1. So I'm going to do like, it might even be too big. This is the secant. Do you guys remember the secant are those u's? So we're just really zoomed in here. So we have part of the u. This is the sine curve curving down. We're only going to graph to pi 4. Okay. So let's sketch our little picture here. So here's kind of, I'm going to change my window to pi first so I can have it right at the end. Something like this. X equals pi fourths. I can't draw that on the graph, but that's a line that looks like this. Now let's label. Which is which? The top is, let's change this to a g of x, would you? The top of is f of x, which is secant squared. This second one is g of x, which is sine of x. And in this case, I already found the integration. It tells me to start at 0, and this boundary line of pi fourths is where it's going to end. So where I'm trying to find the area then is right in there. So once again, if I wanted to find the integral of secant squared from this point, that would give me the entire area between secant and x-axis. I want to take out this area, which is the integral of sine. So I am going to go